Good morning and welcome to the Value of Ground Testing in Wind Energy webinar. My name is Sarah Wallace from Transcat and I'll be moderating today's event. Today we have joining us from Megger 3 representatives. We have Paul Swinard, Power Product Portfolio Manager, Jeff Jowett, Senior Applications Engineer, and David Danner, National Distributor Sales Manager. Then also from Transcat, we have Dan Colvin, Wind Energy Sales and Product Support. Today we're going to be spending half of our time in presentation and then the other half in a Q&A session. If you'd like to ask a question, please send it to me through your question box to the right in your webinar controls. If we happen to run out of time before getting to all the questions, we'll follow up offline with you through the email or phone number that you left with us during registration. I also wanted to mention that this webinar is being recorded and will be available for viewing through transcat.com next week. At this time, I'm going to turn the presentation over to Paul Swinard from Megger.
Hello, good morning. Thank you, Sarah. Today, I'd like to talk to you about the ground testing in wind farms, and in particular, I'm going to run through a schedule here of, firstly, the importance of ground testing, a little bit about why it's performed and what the benefits of the testing it is, and then we'll talk about the sort of equipment which is used to perform the testing. Then, in summary, I'll run through some of the different test methods, what methods are used and why, and then after that we'll have a little look at the sort of ground testing what can be done during installation. In other words, breaking down the system into elements. Ground testing during maintenance follows with a discussion on common issues and the sort of testing challenges we have. And then I'd like to finish with an additional test which with one of our newer products, DET 14C, which is a stateless measurement. Okay, a little bit of background about Megger and ground testing. Megger was actually a pioneer in ground testing. Dr. George Tagg pioneered ground testing method at Megger some well over 50 years ago. We've been designing, manufacturing and selling test instruments for ground testing for over 50 years. And you can see there are some older photographs of instruments in use. Okay, the importance of ground system testing. Why is it performed? The connection to ground on many systems is a very important connection, and it's very important that the resistance of that connection is low as possible. On a power supply system, if there is a fault, the protective devices, the amount, how fast they will operate will depend on how much current is flowing. If the resistance to ground isn't low enough, if your connection to ground isn't low enough, then those protective devices may not operate in the time required and therefore not offer you the protection required. Also, in terms of fault conditions, ground potential rises are another hazard. If the connection to ground isn't low enough, then you can get a step potential across a piece of ground as the current flows through it. You can get a touch potential on things like metal fences or anything which is connected to the ground system which might end up with a potential across it due to a poor connection to ground. And also adjacent conductors can also have a relative voltage between them. In addition to that, electrostatic discharge the protection provided is often totally reliant on the quality of the ground connection, and lightning protection, which is obviously a very important area for wind turbines, is also reliant on a good connection to ground. In addition to that, the ground connection is an effective way of taking any induced noise or any earth leakage into ground, and in a way which prevents problems anywhere else on the system. So overall, there's many reasons to ensure that a good connection to ground is available and a reliable connection throughout over a period of time. With respect to the equipment that is used. Here in the picture you can see a typical 3-pole tester, in that there are 3 connections. The first connection, the X, is made to the earth electrode you're going to test. Second connection is potential. That is connected to an auxiliary spike or probe, which the operator will place into the ground. And then you've got the current spike or probe, which is placed again by the operator, and in this case the instrument is injecting a test current into the ground. Okay, I'm often asked whether or not it's possible to use other equipment. Well, where this varies predominantly from other instruments is how it injects the current. As you can see from the test source here, I'm injecting a square wave, and this is typically 128 Hertz. The reason for that is 128 Hertz is not a harmonic of 60 Hertz. Therefore, if I inject a current into the ground at 128 Hertz and phase lock my voltage measurement into that frequency, then I have a very good chance of ignoring any other stray currents flowing through the earth mass. So the key thing here is that the instruments are designed to cancel the effects of ground currents flowing in the ground. Okay, that particular instrument there, as you can see, is a 3-pole tester. We also have a different kind of tester altogether, a stateless tester. As it sounds now, in this case we're not going to place a P or a C spike into the ground. In this case, this current clamp here will inject a current into a circuit and then measure actually how much current is induced. Now there's 2 cores in the head. I'll find the cursor, here we go. In this head there are 2 cores. One core is inducing the current, and the voltage on that coil is kept constant. Therefore, the amount of current being induced is directly proportional to the resistance of a loop. And you can see here, I've placed the instrument around this particular electrode, and what I will be measuring is this electrode in series with all these other earth paths in parallel. And basically, it's a loop tester, so it's important that you understand where the current is being injected. It's also important to understand that the readings between this instrument and a 3-pole tester may not be exactly the same. However, this instrument will only ever read high, in other words, it won't ever read a falsely low reading. It will always give you a higher than the actual measurement. And also, the amount of parallel paths, the more paths in parallel, the reading drops to the actual value of this electrode. So it's great for applications where there are many current paths to ground. Okay, I'll move on now to the different test methods used. We had a quick discussion there about the clamp, but reverting back to the 3-pole methods, there are a number of methods for doing this. The most common and the most traditional method is the Fuller potential method. As I mentioned earlier on, we're going to put an auxiliary probe in the ground to inject a current. We're going to place an auxiliary potential or voltage probe to measure the volt drop across the earth mass. And then we're going to calculate the resistance simply by taking the voltage and dividing it by the current. Okay. However, we also have to take into account that the ground electrode under test has what we call a sphere of influence. In addition to that, so does our current probe we've placed in the ground. There is also a sphere of influence. And in this, when we're doing this test, we have to make sure the potential probe is not within either of these sphere of influence. Just to quickly describe what that means, if you can imagine the earth mass around the electrode as a series of shells. Let's imagine the shells are all of equal thickness, and as you can imagine, as I move away from my electrode, the volume of earth in each shell is getting bigger and bigger, and therefore the amount of additional resistance being added as I move away from the electrode is becoming less and less. Once you get to the point where the amount of additional resistance is 0 or negligible, that's the point where we would say we're outside the sphere of influence. How do I know whether this potential probe is outside the sphere of influence. Well, I have to do a number of measurements, placing the electrode at equal spacing between the two, the system and the current, and plot the graph. And this is what I would do. As you can see, as I'm moving across, I'm taking the resistance value I measured with the instrument, and I'm plotting it on a graph. Now, when I finish the graph, hopefully it will look a little bit like the graph represented here. It may not be exactly the same shape, but effectively I'm looking for a flat in that graph. The flat area represents the area where I'm outside both spheres of influence. Okay, now typically that appears approximately 62% of the distance between the ground system I'm measuring and the current probe position. Now, to be able to get that flat, I need to have the current spike far enough away from my ground system I'm measuring to get that flat. And typically for a single electrode, I put 15 meters. I'm not sure, I'm just trying to calibrate myself in feet here, but 15 meters would be a typical spacing for a single electrode. If it was a large system of a number of electrodes, or maybe a ground mat or a plate, we could be talking 60 meters. However, the challenge with wind farm ground systems is that they are often huge, especially as a complete wind farm. If I look at a single wind turbine, I can see that the sort of spacing I would require is going to be in the order of something like 425 feet. A 2 megawatt turbine earth system is approximately, across the biggest dimension of the earth system, 75 foot across. And with that kind of size earth system, I need to have the current probe about 425 feet away to be able to see a flat. That's taking into account, variation in the soil makeup, the moisture content, which can vary throughout the year, and we have to take into account those factors when we take that measurement. Effectively, you're looking at quite long lead sets. Now, if there is no flat, as you can see here, I've shown a graph here where I have no flat region. Then the next method I can use is called the slope method, because we don't have a flat area, we only have a slope. Now in this method, it does involve some mathematics, but it's not a difficult test to do. You do 3 measurements with the voltage probe or the potential probe 20%, 40%, and 60% away from the earth system I'm measuring. I put those values into a formula. I won't run through that in detail because of the benefit of time, but you get a value for mu. That value then I will look up in a chart. I apologise for the slightly fuzziness of this chart, but I would take that value, which is 0.47, and then 8, and where that crosses here, I now have a value of 0.632. Now what that is telling me is that if I place my voltage probe at 63.2% of the distance between the system earth I'm measuring and the current probe, at that position I will measure the actual resistance of the earth system. Now the issue becomes greater though if we're going to test a whole wind farm. Now our wind farms are obviously huge systems, and I've actually heard of people running out 2 kilometers plus of cable to be able to take a measurement. In this particular case, in our application department, we did have a inquiry once where somebody was actually using 2 kilometers of cable. Now, in this case, it is very doubtful whether you'd be able to get anywhere near the kind of distance practically to take a measurement. So the slope method would come into its own. The selective test method, which is basically more practical for the substation end of things. Here we have a 3-pole tester, and the challenge here is I've got multiple electrodes to ground, and I'll need to measure one electrode. Now normally the requirement would be to disconnect that electrode from the system. In other words, so it's not connected to any other path to ground, it be either another electrode, connection to another mat or plate, or indeed the building earth connections. Now, in this method here, the test current is being split between all those different connection points, but I'm using a clamp to actually measure just the test current flowing down the electrode I wish to test. So therefore, I'm able to take a measurement of that single electrode without making that disconnection, which has got the advantage of not having to undo potentially corroded nuts and bolts on clamps, the time aspect involved. It has a number of benefits. We also have the clamp on the stakeless method. Now, earlier on in the presentation, I showed you this clamp meter. We also have a 4-pole instrument, which is actually called a depth 4 TCR2, the Mark II version. And this instrument can take 2 of these auxiliary clamps using exactly the same method as this clamp meter on the bottom right. But now we've got 2 individual cores, and it's exactly the same method as I mentioned earlier on, where we induce the current with one clamp and we measure how much current is being induced with the other clamp, and from that we can calculate the loop resistance of that circuit. Okay, that's just to give you a background of the other options available. Moving on now to ground testing during installation. Now, the installation is the only time when it's possible to test and verify the performance of individual elements of a wind farm earth system, mainly because there are no interconnections at that point. We've installed maybe the base ground system on a single turbine, and we can make that measurement. Now, it's important to break the system into elements and test at each stage to make sure we check and verify the effect of the performance of each part of the system. And I certainly would recommend all these measurements are documented to prove that what testing was done, and that you can prove that what you did to verify the performance of the system in case it's ever needed in the future. Now, I would also, when you document the measurements, make sure you include the C and P spike locations, because as the direction of the spikes away from the turbine can change the values, typically if there's other metalwork in the ground in the vicinity. So it's important to log those values as well. We can help you with that in that we have some software which is provided free with many of our instruments called PowerDB Lite, which is an asset management software. But the benefit I want to highlight here is there are a number of forms in the software which you can fill in. But the important part is that you can actually do the calculations. In other words, the test form will perform the calculations for you. So if you give the form the 3 values or 3 measurements for the slope method, the form will calculate the actual position for you. You don't have to do the formula, you don't have to do calculations or look it up on a chart. It does all that for you. And it does that for a number of methods. I believe there's something like 9 forms on the software. And there's test everything from the forward potential we mentioned and the slope method, but there's even less common tests such as star delta, intersecting curves, and even the forward potential method, which I won't go into now, but they're all methods which have their benefits, and you know, you can utilize these methods far easier using PowerDB Lite software. In addition to that, when you're installing a wind farm, it would be also very important to verify the resistance of the lightning protection circuit. That is the resistance from the actual wingtip to the lightning receptor of the wingtip right down to the earth point in the base. Typically this resistance needs to be 25 milliohms or below. Okay, for that we also have a set of test leads, the KC series, but I'll mention a little bit more about those in a moment.